division, a synthetic division is applicable only in a situation in which we have a polynomial at the top and x minus a in the denominator. But of course, this can be x plus 2, it can be x minus 1, it can be x plus 3, it can be x minus 7, and so on and so forth. By comparison, in this case, a is negative 2. By comparison, in this case, a is 1. Can anyone tell us what is a here? For x plus 3.
Negative 3.
Very good. And so on and so forth. So of course here it will be a equals 7 and so on. So in this little box, I will always have to put a. Since it's x plus 2, a is negative 2. So I have to write negative 2. Now the coefficients have to be in descending order. Since the degree is 3, then it has to start with degree 3 and the coefficient is 1. As you see, degree 2 is missing, so I have to write a 0. Degree 1 has a coefficient of negative 7, and degree 0 has a coefficient of negative 6. Actually, this is very simple. But keep in mind, if I have a polynomial divided by x squared minus 3x plus 1, I cannot use this. This requires denominator to be x minus a. And accordingly, I identify a. This does not work with anything but the long division. But the long division works here. So the long division works in both cases. Synthetic division only in this case. Okay, so let's start the algorithm. The leading coefficient always gets copied. And here's what happens next. Negative 2 gets multiplied by 1, and the answer is written here. I perform the operations I see. 0 minus 2 is negative 2. I continue in the same way till I'm exhausting all coefficients. Negative 2 times negative 2 is 4. And I copy the answer above the line. I perform the operations I see. And then I multiply again negative 2 times negative 3, which is positive 6. I write it above the line, and it happens that this is 0. So here's the result. When we divide degree 3 by degree 1, what degree do I get?
Degree 2.
Excellent. Which means this is the coefficient of x squared. This is the coefficient of x. And this is the coefficient of the free term. So then the answer of the division, x to the third minus 7x minus 6 over x plus 2, is x squared with 1 in front, is x with negative 2 in front, and is negative 3. And there is no remainder. It's a very simple procedure, but it has limited applicability, however. So now you were asking about the remainder theorem. Since I could write this, there is no need. But the remainder is 0. If the remainder is 0, then I know that x plus 2 is a factor of this. So therefore, x plus 2 is a factor of, tell me if I'm not in range when I write here. So if you can see, please stop me anytime, okay? So this is the factor of x cubed minus 7x minus 6. Now, the remainder theorem says that if I divide these two, and I'm not interested in the quotient, I only want the remainder. The remainder will be the top polynomial, let's call it P of X, evaluated at A. And this number should be 0 because that's what we got. So x to the third, negative 2 to the third, minus 7 times negative 2 minus 6 must be 0. If not, we made an error. I made an error here. So let's check. Negative 3 to the third is negative 2 to the third is negative 8. This is positive 14 and minus 6. This is negative 14 and positive 14 is 0. Therefore, we also, the same thing we can write again. Therefore, x plus 2 is a factor of x cubed minus 7x minus 6. It's a nice method. I did not present it. I will not test you on this because I didn't present it. I thought that we had other topics that were very important, and I didn't think we would have time to do this. But since you asked, I have to answer. It's not such a big deal. For those of you who fell behind in with homework and quizzes, please check your email. I begged you to finish up the work. Okay, so please read your emails. Very good question. Anything else?
Other than that, I got everything out of 3.3. That was just the only thing, because the book presented it and the homework did. I was just wondering if we were going to be tested on it or not. So.
No, I will not, but is it clear now?
Yep, I understand.
Very good. Anything else? Do we have anything else? Okay, so in that case, I would like to start 3.5. Rational functions. So we agreed that our test 2 will be April 19th, right? From 2 to 4. No one had any objections on that, so I'm hoping we can keep that. So for now, we will be in Zoom. I will send you a file. We'll see how it works. I have a meeting on Wednesday. Wednesday, I may start our class a few minutes late. So please forgive me because we are getting information about from the dean. So I have to attend a meeting with the dean. So it may end up on time for our class. But if I'm a few minutes late, so please, I'm going to email everyone so they know. Okay, very good. Next question. Is there anything else, or can I continue with this? Okay, first of all, what is a rational function? A rational function, RF, is a ratio of two polynomials. We're not going to be cut off school provided licenses for everyone, so we're going to go all the way an hour and 15 minutes with no interruption. Thank God, goodness. Okay, so yes, that is nice, yes. Ratio of two polynomials. So I like to present these polynomial rational functions in 3 different categories. The book doesn't do it like that, but it will be easier for us to discuss it. So the first thing, type 1, I'm going to give you 2 examples, type 2, 2 examples, type 3, 3 examples, and we'll discuss the difference between them. So we understand why I call this type 1, 2, and 3. Okay, type 1. let's say x plus 1 over x minus 1. Let's say x squared minus 9 over x squared minus 16. Type 1. Type 2. Let's say f of x equals x over 1 plus 2. And another example, x over x squared minus 4. These are just examples, but we want to discuss them. And for type 3, f of x, for example, is x squared minus 4 over x plus 1. And another example, x cubed minus 1 over x squared plus 1. So let's look at type 1. We'll look at these two examples for type 1 and say, by comparison to the other two, say that type 1 must have all functions, rational functions type 1 must have a property. What do you think they have? What is the property that these two have? For type 1.
All the exponents are there. It's not missing anything.
No. So for example, here degree is 2, but there is a missing term. So the category is all these functions in type 1 have same degree over same degree. So all rational functions that have degree 1 over 1, 2 over 2, 3 over 3, 4 over 4, same degree over same degree, are of category type 1. Okay, let's look at category 2 or type 2. What can you say about type 2?
It's degree 1 over degree 2.
Yes. So in other words, higher degree in the
Denominator.
yes. Excellent. That's the property. Higher degree in the denominator. It could be 1 and 3, 1 and 10, 2 and 4, 5 and 9. It doesn't matter. It's higher degree in the denominator. Perfect. Let's analyze type 3.
Higher degrees in the numerator.
But exactly by 1 unit. This time is exactly by 1 unit. So the denominator has degree n, whatever that is. And here is the degree n plus 1. Degree 2, degree 3, degree 5, degree 6, degree 10, 11. For type 3, I will not ask you to graph them. I will graph you one. I will show you how to graph one. But I will only ask you something about it. I don't think we see too many applications of type 3. But we see applications of 1 and 2. And we're going to get to applications after we graph at least 2. And then we'll look at applications of these functions. Okay, so let's start with the first one. Before we start, I would like us to go back to the list. So we want to graph. And we're going to start, let's say, with the first one. X plus 1 over x minus 1. Okay, remember there was a long list of items that we had to go through, or steps if you'd like, when we graph polynomial functions. A lot of those will transfer here. Number 1, domain. Number 2, X-intercepts and their multiplicities. Let me know if I'm not focused here. Number 3, a Y-intercept. Number 4, these are not new. Number 4 is new. Vertical. We have never seen this before. Asymptotes. And behavior near the vertical asymptotes. New. This is totally new. Polynomials do not have asymptotes. I'll explain. As you know, as you would probably expect, it will take us 20 minutes to graph the first function and then 4 minutes or 2 minutes to graph the next one. But the first one needs a lot of explanation. 5, horizontal asymptote and end behavior. Horizontal asymptote and end behavior. This is totally new. From here on, everything is known. Range, symmetry, max min, if any. But this is with TI-84. That's pretty much it. So 2 new things. Something called vertical asymptotes or vertical asymptote and something called horizontal asymptote. I'm going to make some corrections to this or I'm going to add some amendments here later. But this is pretty much what we need. We are back to our function. F of x, x plus 1 over x minus 1. No matter which order you present anything, you must start with the domain. This is not the actual carved in stone sequence. It doesn't matter. But this is a must. It must be the first. Okay, then. Can anyone give us the domain of this function? And get the chart or the table going.
Negative infinity to infinity.
Careful.
Negative infinity to negative 1 and then 1 to infinity.
But you mean 1, correct?
Yes.
Perfect. Yes. Negative infinity to 1 and 1 to infinity. Very good. The domain is done. Okay.
Can you push your paper up a little?
Yes. Thank you. Sorry, you'll always tell me because I'm looking to the left. One computer is recording. I'm looking to you, and I'm also looking at the what you see. So my apologies. Keep track of what I'm doing. Okay. So when a rational function is undefined at a point, like for example at the value of x equals 1, there is an exception. We're going to talk about the exception. But for now, I'm going to say that when a rational function is undefined at a point, at an x value, x equals this number is a vertical asymptote. Let's explain the concept of vertical asymptote. at x equals 1, there is a vertical line called a vertical asymptote. Why is it? Because this function is undefined at this point, the function cannot cross this line anywhere. What can it do? It can do this on one side and this on the other. It can do both on the positive. It can do both on the negative. It can do the negative on this side and positive on that side. There are 4 possible options. So it doesn't touch it. It gets closer and closer to it. On this side going to infinity, on this side going to negative infinity. And this is the concept of a vertical asymptote. So the function is undefined at 1. It will have a vertical asymptote at 1. And I know for sure that left and right will be infinities, but I don't know the sign. How do I determine the sign of the infinities? Using a number that I'm not going to plot. Using a number close to 1 on the left-hand side and close to 1 on the right-hand side. So let's plug in 0.9. When I plug in 0.9, what is the sign of the numerator? Just the sign. How much is 0.9 plus 1? Sign. What is the sign of the outcome?
Positive.
Good. What is 0.9 minus 1? Just the sign of the outcome.
Positive.
Negative.
Right? 0.9 minus 1. So what is the sign of the...
I did 1.1 minus 1.
No, we're not there yet. So I cannot plug in the top 0.9 and in the bottom something else. So when x is 0.9, the top is positive, the bottom is negative, correct?
Yes.
So positive over negative has what sign? What is the sign of the outcome?
Negative.
Perfect. With 1.1, please plug in 1.1, top and bottom, and tell me the sign.
Positive.
Very good. Because 1.1 plus 1 is positive, and 1.1 minus 1 is also positive. Positive over positive is positive. Agreed? So,
yes.
We determined the vertical asymptote. In this case, it's only 1. And we determined the behavior near the vertical asymptote. Just one vertical asymptote, and this is the behavior. It means that the function will do this on this side to negative infinity, and this on this side to positive infinity. So let's go back. I'm done with this. I'm done with this. I want to determine the x-intercepts, the y-intercept, and move on. Okay, so how do I determine the x-intercept for any function, including this one?
You set the numerator equal to 0.
So the function equal to 0, or x plus 1 equals over x minus 1 is 0. Very good. A fraction is 0 only when the numerator is 0. So x plus 1 equals 0 means x equals negative 1. Since it's multiplicity 1, what will the function do at negative 1, 0? Will it cross? Will it turn? Will it cross slowly? Will it turn slowly?
It'll cross.
Very good. Just a regular cross. Very good. So now we want to find the y-intercept. How do I find the y-intercept for this function or any function?
F of 0.
F of 0. So 0, 0, 1 over negative 1. How much is 1 over negative 1?
Negative 1.
So 0, negative 1. So we accomplished everything so far. All these are done. The domain x-intercept, multiplicity, just 1, a y-intercept, vertical asymptote, and the end behavior. The range, we'll have to graph it first. Max-min with the calculator. Symmetry, we're going to talk about in a minute. So I'm finally down to finding the horizontal asymptote. Okay. I'm not going to ask you all the time to do this. I will not, but I need to explain how we get to the horizontal asymptote and the end behavior. So the end behavior means here. What does the function do when x approaches negative infinity? What does the function do when x approaches positive infinity? This is the end behavior, like we had before with polynomial functions. In this particular case, this function is type 1. I will give you the final result or the shortcut, but I want to explain how to get there. So the function is x plus 1 over x minus 1. X plus 1 over x minus 1. What is the degree of the numerator? Yes, I will factor out x. And you should say you can't. And I will have to say you're right. However, I can force it. As long as I write this, I'm okay. Because x times 1 is x, and x over 1 times 1 over x is 1. I will repeat for the denominator, factoring out x like the numerator, so then I have 1 minus 1 over x. Is this true? Yes, it is. X times 1 is x times negative 1 over x over 1 times 1 over x is negative 1. I will simplify these two, and then I'm going to ask you, where does this go? It's not the equal symbol, as x approaches infinity or negative infinity. Well, this is 1 over 1, but let's see where these go. So imagine I have a cake, and I divide it by 2 people. You get half, I get half. If I divide a cake by 10 people, then you will get much less. You will get 1/10. If I divide a cake by 100,000 people, you will get almost nothing. I will get almost nothing. If I divide by 1,000,000, I will definitely get nothing. So what the point I'm making is, when x approaches infinity, this piece is so small that it doesn't matter. So the whole thing approaches 1 over 1. So this is the horizontal asymptote and the end behavior as well. And here's the shortcut. So here's the note. For type 1, the horizontal asymptote is y equals leading coefficient over leading coefficient. What is the leading coefficient? So you don't have to do it like this. I'm not going to ask you to do this at all, ever. I just want you to see how we get 1. So what is the leading coefficient of the top?
1.
What is the leading coefficient of the denominator?
1.
That's the reason why only for type 1. Only for type 1. Leading coefficient over leading coefficient, and this is the horizontal asymptote and the end behavior. Okay, what is this horizontal asymptote? Okay, here's what it means. It means that eventually, when x goes to infinity or negative infinity, the function values will get closer and closer to 1. Not in the middle, but far away. When x approaches infinity and when x approaches negative infinity, the function values get closer and closer to 1. Why? Because y equals 1 is a horizontal asymptote for this function. Okay, so the symmetry in this case, if there is a vertical asymptote at 1 and there is no vertical asymptote at -1, the function cannot be symmetric. But I have to write. So I have to write like we always did in the past. I have to write that f of negative x does not equal f of x, and it does not equal negative f of x. Not symmetric. Just to show that my professor, then I know what I'm talking about. You don't have to calculate anything. This is good enough. Any questions on this? Okay, we are ready to graph this function now. And then look at other examples. When we graph a function with asymptotes, we have to graph the asymptotes first. Like in the past, I don't care about anything but what the table is telling me. The table tells me to graph a horizontal asymptote, y equals 1, and graph a vertical asymptote, x equals 1. They are not part of the graph, but they have to be graphed. After I finish with graphing the asymptotes, I will plot the points I have. And actually, I only have 2 points. -1, 0, which is this point, and 0, -1, which is this point. And now let's take a look and see what the table is telling us. When x gets very, very small, the negative, or very big negative if you want, the function comes from 1. Okay. It crosses at -1, 0. It crosses at 0, -1, the y-axis. And on the left-hand side of the vertical asymptote, it goes to -infinity without touching it. That's what this is telling us. From 1 crossing the x-axis, crossing the y-axis, going to -infinity. On the other side, it says come from positive infinity and approach 1. So this is the graph of f of x, x plus 1 over x minus 1. Any questions? Well, obviously, this is the first example, so let's look at another one. Type 2 is even easier. How come? Let's write what happens for type 2. Everything identical, except y equals 0 is always the horizontal asymptote. So leading coefficient over leading coefficient is only for type 1. For type 2 is even easier. I don't even have to think. It's just y equals 0. If you want me to show y, I can show you y.
So what?
Yes? Did anyone say yes?
Yes, I did.
Yes.
Oh, very good. Perfect. Okay, so let's say we have x minus 1 over x squared minus 4. Is this type 2?
Yes.
Yes, it's type 2 because the degree in the denominator is higher than the degree in the numerator. Very good. So, like before with the explanation we looked at a minute ago, let's see what we have. What is the degree of the numerator? Disregard the denominator for a moment. What is the degree of the numerator?
Oh, is it -1?
The degree.
No. 1.
1. So I factor out the degree. Like before, I have 1 minus 1 over x. Forget about the numerator. Now please tell me what degree we have in the denominator.
2.
Yes, in this case, I have to factor out x squared. Like before, I have 1 minus 4x squared. How come? Let's check. X squared times 1. X squared over 1 times 4 over x squared is 4. I will simplify by 1x, not more, at this point. As we analyzed 5 minutes ago, where does this go when x approaches infinity or negative infinity? 1 cake divided by 1,000,000 people. How much will I get?
approaching 0 and
X.
negative.
Very good. Where does this? No, 0 doesn't have a sign, right? So where does this go? 4 cakes divided by 1,000,000 squared. How much will I get?
So approaching infinity.
4 divided by a huge number. Let's divide 4 by something like this. What will I get?
Next to nothing.
Exactly. Good. So all this will approach 1, but I have a 1 over x in front. Where will 1 over x go? So all this goes to 1, but I still have a 1 over x in front. And what did we establish? The 1 over x always goes to
0.
whenever x approaches infinity, not when x is 5. If x is 5, I get 1 over 5. But if x approaches infinity, this approaches 0, this approaches 0, this is 1 over 1, but unfortunately I have a 1 over x in front. So that's the reason why every time the denominator is stronger than the numerator, has a higher degree than the numerator, the answer will always be 0. Is that clear? Perfect.
Yes.
Let's look at an example now of type 2, which is easier than type 1. I don't even have to... let me look at my video just 1 second. Let me stop this because it took me more than an hour to upload that.